All right, everybody. Good morning. So let me check. So last Friday was the withdrawal deadline, I believe. Uh, Calm down a lot. So uh, my point is, I don't know how. So is my like teaching style is not accurately reflecting to your expectation or something else? What? What is that? Any comments? Oh, you didn't understand. So people withdraw. It means something went off. Something went off without their expectations. What exactly the expectation you are coming like, to the class? Mhm. Okay. Ah, okay. Oh, I I forgot to migrate the lecture 10th quizzes to here. So in this, I think now you have lecture 10 practice questions, which I forgot to migrate to here. So in this one, and you are going to practice what exactly I'm going to ask you in the final exam, which what kind of question you may see. I'm going to give you three question styles. Simply is the code generations. It purely based on your homework three, which is our lecture 10 and homework three, and I'm going to ask you what is the instruction at index what. That's it, nothing else. So for example, in the first question, it is just saying in homework three's grammar and blocks, possibly you could write some pseudocode in your cheat sheet, which I'm allowing that. And you are going to compile a PL0 program and answer the question below, which is this is our program. And I'm possibly going to randomly select what is the index I'm going to allow you to do. So the first instruction you are going to generate in your homework three, which is 703. That's that is the thing, but it's living in the index zero position. But in coming to the index one, it could be possibly most likely to be inc05. Why is 05 variable 2? So purely translating into our digits representation could be 0 or 605 if I remember correctly. And then let me submit it. Oh yes, 605. Increment 0.5, 5 slots for the activation record. So that is a typical question you may see on the final for the lecture 10, which is purely based on your homework 3. But once you come into homework 4, it's getting more interesting, more complex, and we're fine to do that. And we have more lexicographical levels to do, and somebody is misimplementing the mark, which you will experience a lot difficulties while implementing homework 4. Okay, so that's the thing. But how about lecture nice questions? Have you practiced on that? Not necessarily. Let me see. Okay. Not really in a good shape, but I would encourage you to practice on the question lecture nice questions. Otherwise, I simply do not or reject any complaints about I'm not providing enough resources to you. Okay. Now I'm accepting all the complaints you have. I'm giving you all the questions you may practice, and which is legitimately to be the final exam questions. Okay. And even for this week, I'm going to publish about 3 different practice questions, which is 11, 12, and 13. And today we are going to finish our 13, the loaders presentation. All right. Any other question? And do you have any complaints on homework 3? By the way, if you didn't submit your lex.c, it's going to come with a penalty. And we have specifically said lex.c and the parser code in C is an integrate part. If you're missing one, it will come with a penalty rather than assigning a 0, it will be coming with a penalty. Okay? Anything? Any complaints about homework 3 instructions, etc.? And if I further could possibly improve your homework 4 instruction? Anything? No? All right. So that's not the thing. Let's coming back to the lecture. So last time we landing on this page, if you still remember the bootstrapping, what is exactly the bootstrapping we talk about in this sense, in our context? And what is the difference between this bootstrapping with that bootstrapping we talk about in statistics? Yes. I see. So that is the thing we have talked about the bootstrapping. But any other answer I can get? No? So what is the bootstrapping we talk about in this context, and how is going to compare with what is the difference between this bootstrapping in computer science and that bootstrapping in statistics?
Well, bootstrapping here is that it's kind of the PC starts with a rudimentary operating system, which will load in something else, and that will load the operating system to try and get the operating system in because the PC can't do it from the beginning. That's kind of bootstrapping.
Somehow. Any other things? Yes. Yes. That's what I'm seeking for, but in general form, what we call bootstrapping in our context is using a very small program to load a larger program, and that larger program will allow us to load the entire operating system that could function completely by its own. So that is the idea of this bootstrapping in our context. But what is the bootstrapping in statistics? We touch on that. Anything? No? So in statistics, what we have here is what we call bootstrapping is not necessarily relevant to your current course, but it's good to know that bootstrapping is pulling samples from the data set, which we train possibly a machine learning model on that. What is the bootstrap? The pulling of samples means, it means we are pulling a subset of that data set, okay? Why it is working is that the data set itself has a specific, a typical distribution. It could be normal distribution, it could be binomial distribution, etc. It doesn't really matter. But when you pull randomly of the subset could be representing that normal distribution. And what our machine learning model is trying to learn is that how that distribution happened, what is the likelihood of that entries belong to certain distribution form. That is the thing your machine learning model is trying to achieve, your deep learning model is trying to achieve. So that bootstrapping is basically pulling samples from the data set and train your machine learning model. That's it, okay? So that's everything I can teach you. So once you got me coming to a real machine learning model or deep learning model class, you will learn in detail. So, okay. Now, what we have here on this slide, which is showing a diagram, shows the first stage of bootstrapping process, which we talk about it. And when the computer is from completely powerless state, and when it's powered on, the CPU begins the execution at a fixed address stored in its hardware. That address points to a small boot program, which is located in ROM, which the ROM is abbreviation of read-only memory. So where ROM is non-volatile, and it means it retains the boot code even the system is powered off. So the boot program's task is to perform a very simple I/O operations, operations to locate a secondary loader, which is labeled here as loader 2 on the storage devices like a hard drive or CD-ROM, etc. But the program this loader 2 is far smaller than an operating system, but it is powerful enough to read sectors from the disk into the memory, okay? At this point, you are still not running the OS. You are only transferring the loader 2 from the storage into the main memory so it can take over the next stage of the process. And once the loader 2 has been located on the disk, this boot program simply loaded or copied it into the main memory. As you can see here, we have loader 2 present. And now the loader 2 becomes the active code that the CPU will execute next. So loader 2 has more sophisticated functionalities. It can understand the file system, devices, interfaces, and the layout of operating system on the disk. It simply know where's the header of the operating system form and how we can load it and what we can load for the operating system file. So now you can think the boot program in the ROM as the smallest spark that just spark enough to initiate the next layer. So the next layer we're talking about here is loader 2. Loader 2 is the flame that grows larger enough to bring the operating system itself. Now, what we are talking about operating system in functionality, it means your car is running, okay? Your engine is running. So this design is very elegant because the ROM space is limited. We know that. And so only the minimal code is stored there. The rest of the logic is fetched dynamically into the memory when the system boots. All right? So here we see a simple pseudocode example of how loader 2 operates. So in older computers in ancient time, it's not really ancient, but in ancient computers, the operators, which is humans, will have to manually key in programs like using a front panel switches, just switching up the switches to make sure that everything loads up. But here, what we have here in the modern computers, we have loader 2 will automate that process. So what we have here is a pseudocode. So location counter, which is called LC, starts at 0, indicating where in memory the next instruction should be stored. So then the program repeatedly reads the data from the input devices and store in the memory, and each increments the LC each time. So then the loader detects the end of file. End of file condition, it knows the operating system has been completely loaded into the memory. At this point, it simply sets the PC equal to 0, effectively jumping that starting address of the operating system. So this is simply a short loop that just shows how the simple steps can prepare in full operating system for execution. Any question? No? Good. So now you can see the final transfer of control, which is loader 2, that is already in the memory, performs another I/O operations, which is bringing the OS from the disk into the memory, loaded to the memory. And once all OS components are loaded, loader 2 hands over its control to operating system, so it's nothing else to do, and the operating system is going to in charge from now on. So from this point, the operating system is in charge and it initializes the device's drivers, such as what is driver C, driver D, driver E, etc. Even in your Linux, what is the main driver you're dealing with? And it sets up the process management. It begins to create the runtime environment for users' program. And in modern computers, is corresponding to what we call a bootloader stage. So if you happen to know that, in Linux, what we have in the bootloader is called GRUB. And for Windows, what we call is Windows Boot Manager. If you happen to know that, that's awesome. If you don't, that's the knowledge you could understand, which is loading the kernel and start the system services, such as we have a Bluetooth interface. We need to initialize the Bluetooth driver to make sure that it is working, and Wi-Fi interface. Well, we have to make sure that the Wi-Fi interface is working. It can scan the Wi-Fi environment, what is access point we can access, what is the password for that, etc. So that's all system services, okay? What we have here is just a summarization of bootstrapping sequences. I just simply summarize everything into step 1 to 3. Step 1, we have boot program in ROM that checks the hardware, ensures that essential devices in like memory, storage are ready. And secondly, we have the initialize operating I/O operations to load the loader 2 into the memory. And step 3, which is loader 2 is functioning, that loads the operating system and pass the control flow to the operating system. So once the OS gains the control, it creates environment where user programs can run. And it loads the devices, drivers, sets up interrupt handling and manage the memories and scheduling. So scheduling is the one thing that you are going to study later in the future of the course. So you will learn about why we have scheduling. Just consider currently every modern operating system is multitasking operating system. It's a multitasking environment. If we do not have scheduling, it simply means how can we managing the process, scanning one process to the second process, third process, can we run it simultaneously? It's all depending on the scheduling part. In essence, we have here is bootstrapping is a process of bringing the machine from a powerless state to a fully operational computing system, a self-starting sequence that mirrors exactly the same recursion idea we saw before, which is simple instructions building towards a complex behavior. All right. So now we have seen here is how the loader and bootstrapping process bringing the operating system into the memory. And we can talk about what exactly the operating system is actually doing. We have to understand what exactly the operating system is. And operating system, the OS, sits at the center of all system activity. In managing the communication between hardware and software, it acts as a traffic controller and decide when the programs can use CPU, memory, and I/O devices, such as your keyboard, your camera, your microphone, etc. And in this diagram, what we have here is OS is coordinates among the keyboard, the mouse, display, the printer, the disk, and the applications. When you press a key, for example, you press the W, and OS simply capture that event, delivers to the right programs. The W can functionality all kinds of things. In your game, W means moving forward, but in your text, it simply types a word, a character, W, okay? And when an application needs to save a file, the OS will handle that disk operations. It'll open as the handler of disk operation, write or read something. That's I/O operations we have. Basically, the OS is controlling everything. Essentially, every modern computer relies on OS as a layer that abstract the hardware and hardware complexity, allowing the user and application to interact the system seamlessly. So without OS, you simply need to go writing instructions. For example, I want to use the memory for now and how many slots I needed. And I'm going to use the mouse for now for clicking and clicking right here. You have to specify everything, but operating system is doing everything for you right now. Okay. Now, once the operating system has the full control of the computer, it begins to manage and execute the programs. A program, what I mean by here is a program on disk is like object file or a executable file. It's simply a static sequence of instructions, okay? When the OS loads that program into memory and allocates the necessary resources to it, it becomes a process. Now could be a question you coming to your final. What is the difference between a program and a process? We just talked about what is the difference between a program and a process. Yes. A program creates a process? No. Anything?
When it says if there when program is loaded, a process is created. So a process could be the I think it's kind of taking the program and like actually processing that through the CPU that executes the commands.
No.
Process is the right program. So a program is a sequence of instructions that pertains to a task, and the process is everything that's on top of it, including the heap space that's allocated, the code that is telling the computer that this is where the program.
Nice. That's exactly the explanation I'm seeking for. But instead of giving you a free response questions, I'm going to ask you to select the correct answer or true or false. So basically, a program is a static sequence of instructions. It is just a file sitting on your hard drive and nothing else. It's just a file. Nothing very special. But its process, it means it's a lively program that is basically running. It's a live program that can do multiple different things, allocate memory spaces and doing stack manipulations, local device, even having some input from the user's output to the screen. That's everything it can do. That is the process we're talking about. Again, a process is not just a code. It's a running instance of a program. It complete with a memory space, registers, and system state. So for example, if you look, just simply open up 2 copies of your web browser, and each one runs a separate process, even though they share the same program file, okay? Now 2 instances. The OS is responsible for creating, managing, and scheduling those processes so multiple programs can run smoothly at the same time, all right? So now, what do we have learned about everything about process and everything? And we have to understand how we put an informal definition of process. Process can be defined as a program in execution, simply as that. Program is just a file, and process is a program in execution. That's it. An activity, an active entity, rather than static code. That's it. And it's synchronized. It means it runs independently and it can be interrupted, paused, and resumed by OS scheduler. Conceptually, you can think that a process is a locus of control. It's flow of execution that moves through the program instructions. Each process is represented by a data structure, which is called PCB, process control block. The PCB stores essential information such as process ID, CPU register, and CPU register values, and the current state, and pointers to the memory areas. So the OS will use this information to suspend one process and resume another without losing progress. Alongside of PCB, what we have here is another thing, which is called PAS. That is a process address space that holds the program's code, the data, the heap, the stack. That together, what we have here, the PCB and the PAS, defined what a process is, a running program with its contents preserved by the OS. So what do we know about PCB? We have to understand what exactly a PCB is. So PCB is the heart of the processing management in operating system. Every active process has a unique PCB that holds all information that the OS needs to track and manage. So this includes identifiers like process ID or name, process ID and name, and base address of the program, and pointers to the next PCB in the scheduling queue. And it also stores the CPU-specific data, such as instruction pointers, stack pointer, and contents of registers, which allows the OS resume a process exactly it left over or left off. Then the PCB also contains the process state, whether it's running state, ready state, or waiting state, various flags or for the interruption and protection modes. So you can think of this one as a process resume card. So when the CPU switches from one process to another, the OS simply saves this current process context in PCB and loads the next process context. So this mechanism will enable the multitasking to happen smoothly without losing any process progress. Just think about what you have here on your phone. You have a lot of programs you can run in every single time. You can switch back and forth. That switching back and forth is basically this is doing the job. PCB is taking its job and saving the state and loading another program state. That's it, simply as that. What we have here is a diagram shows how a process is created. And when a user runs a program and the operating system simply loads that program from the disk into the memory, making it become a process. Then it allocates the necessary information as CPU time, memory regions, and I/O handles, and it creates corresponding PCB to manage it. So the PCB links the program's code and stack of the OS scheduler, forming the complete process. Essentially, OS is transforming a passive program file into a living process ready to execute instructions. The PCB itself acts a OS control handle for that process, while the code and the stack together defines the behavior and the runtime state. This is the starting point of the process life cycle for lifecycle management, which includes creation, execution, suspension, and lastly, termination. Okay. So here is expanding the process creation steps into more detailed diagram, I would say. On the right, what you can see is object files stored on the disk. What are the things we are storing on the disk? After assemblers, every object file is storing in the same way: header, data, text section, and symbol table. Everything here is living on your hard drive, nothing else. And once we transform this one or load it into memory, the loader is doing its job, the operating system is doing the job, it creates a dedicated space, which is called PCB. And what we have here is the data will be loaded as data and the BSS. So what exactly the BSS is, we will talk about later in this lecture, so you don't have to worry about this. And we'll talk about what exactly the data is handling, but simply as the data will be copied into these sections. And the text will simply go to the text sections in the PCB. And this entire thing here, this table, will be calling at PAS, process address space. Nothing really special. Yes.
Program or when that process is waiting.
Is the program in softwares? It simply is a state, a saving, or just you can think it's a file. Nothing really special in living in memory. It is not a program. PCB is not a program. It's the same one. Yeah. Depending on what operating system you are using, but conceptually they should be kept the same. PCB should be kept the same. Otherwise, the operating system may use a different strategy dynamically to read this PCB along to another PCB, which changes its format dramatically, which you don't want. Possibly could create confusion to the operating system, which is what exactly it is. I have to use a different strategy to load this PCB along to another PCB, which is not possible for the OS. Any other question I may have? Good. Okay. Now, let's come into the how the memory is organized. What we have talked about the PAS. This is the PAS at the runtime environment. That is the process address space that is also called runtime environment. So every process has several key sections. That is at the bottom, we have text sections, which holds the program executable code and is typically read-only to prevent accidental modifications. That's simply what we have done in your homework 1, the virtual machine. You have text sections, you have stack section. We simplified this idea into only 2 things. You only modify the text sections once you load. So once you fully load that instruction into the text sections. Other than that, you are not going to modify the text section at all. You only access it. You only read the information from it. So it's read only. Then we come into the data section. The data section segment contains initialized, global, and static variables, while the BSS segment holds uninitialized, global, and static variables, which is default set to be 0, okay? Heap growth on here is upwards as the program requests the memory dynamically through the functions like malloc or new, and stack grows downwards, storing the function calls, frames, local variables, and parameters. Then I have a question, very interesting question to ask you. Is the direction of stack and heap matter? You sure about that? Does it really matter? It doesn't. It doesn't. It doesn't really matter. So simply as what we have in homework 1, I can simply change the stack growth from left to right to the left, whatever the direction. And simply it's an implementation-wise choice. I can have the stack grow 500 to 0 or 0 to 500. It's purely based on my choice. Stack operation is the most important. Store and pop it out. That's it. Okay? So the most important is the data structure, not the direction. Okay? And how about heap? Is the heap truly growing with some directions? I have seen, no. You are correct. No, heap is not necessarily have any directions. We have talked about this one heap in the last lecture. How can you visualize a heap? Come on. How can you visualize a heap? You have multiple memory fragments living in your operating systems, and those fragments is available to use. Heap is basically linking them together. That would be it. So is the direction matter? In this sense, it doesn't really matter, okay? So what we have here is simply everything together is a region defines the working space for a process. The structure is fundamental to how functions call each other and how recursion works and how global versus local variables are being separated here. It allows the operating system to isolate each process and safely managing the multitasking, okay? So on this slide, we simply zoom into the stack portion of the process. But beforehand, we have talked about BSS. We have talked about BSS a lot, but what exactly the BSS stands for? So BSS stands for block started by symbol. That's it. This comes from early assembly programming and referring to the segment used for uninitialized global variables. But here, our focus is on stack rather than the BSS. You simply understand that BSS is simply for uninitialized global data, and data is for what? Data section. What's that? Initialize the data. That's it. That's the only difference you should think of. So what we have here is that demonstration is that we have a sub function is called a new stack frame is created. What we have talked about stack frame is what? In your term is what? Activation record. That's it. Each frame holds its function So local variables is parameters, like return address, is dynamic link, is static link from the previous frame. For instance, what we have here in this example on the right, the variables list and sum live in the stack frame of the sub function, and sub returns that the entire frame will pop from the stack, which is basically removing that activation record from the stack, and the space will be reclaimed. And stack management is exactly what we have done in homework 1, if you still remember. And coincidentally, it is exactly the same direction you are dealing with in your homework 1, going downwards. So from 500 to 0. So this mechanism is what enables nested function calls and recursions, and each call gets its own isolated workspace, preserving the program state and execution order. So this system works beautifully, but it also comes with the most famous vulnerability. So that's the thing I want to just mention about here. Vulnerability is what I have studied for a long time. Simply, I just want to touch on that. So I write here a program, if a program writes more data in the local buffer than the stack frames allow it, is access can overwrite the nearby memory. So simply overwrites another activation record. For example, what we have here is we have just 6 slots of locals. And if an attacker comes in and writes more locals, and those locals override a different activation records, for example, return address, and this return address could allow that activation record to return to a different memory slot, memory locations in your memory. That memory location could be the starting point of a malicious code. It means it has full access control of your entire operating system. This vulnerability is called stack-based buffer overflow. It will not become a question in your finals, just simply for interest. If you happen to know that, it's awesome, okay? So those attackers can exploit by injecting the malicious code or redirecting the program's flow to a different malicious code. It could be elevate the access control of your entire OS. So in modern operating system, what we can do for defining this one is we can use something called stack canaries or non-executable stack regions, or something as address space layout randomizations, which is called ASLR. So what I'm trying to emphasize here is stack is not something that the programs can work in that space. It's also very important to understanding how we can secure it. Question? Okay, great. Any question for that? Great. Now, what we have here is a different loader. So previously we talked about absolute loader that works well. And works well for each program that has a fixed memory address. But in modern systems, we have to run multiple or many programs at once. We could have on your computer, well, I'm currently doing right now. I have Canva for presentation. I have Zoom for live streaming and etc. We also have Outlook for email, and I have a Slack for communication. A lot of things happening is multitasking. But the thing is, the absolute loader, every program had to be assigned to a unique fixed address. It could be tedious. It could be limiting its flexibility. So that is where what we have here is relocating loaders come in. So a relocating loader can load a program into a available space in memory. It automatically adjusts space references inside a program so that it runs correctly no matter where it is placed. So this allows multiple programs can coexist and share the system resources without any conflict. For example, if one program may have a starting point of address of x200, and while another starts as x400, and both can still function properly. And relocation is the key feature for multitasking and memory management in the modern operating system. What we have here is a slide to introduce how relocation is represented in the object code. When the assembler generates the machine code, it assumes the program begins at a base address, often we call 0. So, however, in this assumptions may not hold once the loader decides to load this program and place it into a memory, such as 400, 500, 600. So it could be different. Yes, question? Yep. And what we have here is to make the relocation possible, the assemblers embeds a set of relocation bits alongside its text sections. It means alongside the text segment, we have a separate table to represent relocation bits. When we talk about relocation bit, is each bit is corresponding to a portion of instruction that contains address. A location bit is equal to 0. It simply means we have no change on that. But once we come into 1, it means we have to adjust this space address to a different slot by its offset. What do we talk about here? Let's take this example. So the location, originally, assemblers think everything starts at 0. And we are calculating the relative spacing from the previous lecture, the assembler lecture. And relocation bit is 0, 1, 1, which each corresponding to a original text segment in here. This 0 corresponding 13, 1, 33, 1, 4, 35. So each pair with good is the same color. And the location number is basically what is the offset we are dealing with right now. And what is the new text segment we are going to use eventually for the program to run. And how we do the calculation is 0 for the 13. It means 0 means we should not change this text at all. So therefore, the new text is preserving the 13 as is. 1 means we have to change it. We have to change the 33. By how? 33 plus 40 times 1. 73. Okay. How about the next one? 1, 35, 40. 35 plus 40 times 1, 75. That's it. Simply as that. Then we come into here is the entire relocation process applied to a full program. In the first column, first snippet here is basically telling you, the source program is written in purely digits, but purely digits we are only having here is copy, address, simply considered as PL0. PL0 we have opcode, lexicographic level, and M. That'll be it. So opcode, do we necessarily need to change the opcode for the relocation? No, opcode is a fixed binary representation for that opcode. We don't want to change its space. It's not addressing applicable. But then we come into addresses. The addresses is 0 and older. Where's the 0 coming from? Is 0 coming from here? Then is assembler we are using the relative spacing to calculate that. That is 33. 33. 35 older. 35 here. All right, simply as that. But now we have the relocation bits with alongside with text segment as 0, 1, 1. Simply we apply the previous calculation. 13 preserved 1 using the 40, and that's 73, 1, 35, using 30 with 75. Then once we coming back to checking after relocation, it means everything will be relocated, even with the data section. The data section 73 is 0 and 75 is older. So we're fine, we're good. So in the final, you could see this source program initially. And I may ask you a question that, what is the before location? What is the text segment for the first instruction, the second instruction, the third instruction, etc. And I'm going to ask you consequently to be, what is the relocation base for this? Okay, yes. You will see a practice question. It will be something like the source program, and nothing will be provided at all. So only thing I will provide is opcode, okay? Opcode text representation. You will see a exact final exam practice question like this one. All right, don't worry about it. Now we come into the this slide, which is talking about okay, what do we have for the relocation? We think about relocation like data section is alongside the test segment. It means it works, but it has a practical weakness. It will when the relocation bits are interleaved with the next the test section, the loader simply must read the instruction code and the relocation data alternatively. It means it has to switch its bits around, so which could slow down the loading process and complicate the parsing. So in modern system, we solve this by separating the relocation data into its own contiguous region. That is called relocation section or relocation map. This section is essentially a list of patched points. So the memory address inside the program that must be modified and is loaded. So each entry specifies where to add the relocation offset and what size of the effective field is. In executable format like ELF, the relocation section follows the text and data sections, which you will see a diagram later of the slides, and the header sections of the object code object file will tells the loader the starting address of the length of that sections. When loading happens, so the OS will simply copy those text and the data into the memory first, and it reads the relocation section and applies each modification and applies those things in one pass. This design will be much cleaner and much faster, as you may see here. And this is the final diagram that summarizes the structure of the modern object code file, which is ELF format used in Linux system. At top is the header, and we have text sections and data sections. Simply, we are moving those relocation information from the text section placed into a relocation section, a dedicated section for the relocation information. That's it. So that's the end of this lecture. Do you have any other question I may have before you leave? If not, so that's it. Someone is playing on the Zoom. Thank you for coming. Have a great day. And I'm going to have a attendance.